Hey, welcome to the last of the presentations on modelling from data, and this is called law determination. And let's have a look at what we've been doing. Just come up here now, and we've been looking at trying to fit a straight line to a set of data. And just remembering, we've gone out of Y and X land into an actual mathematical model where we're describing a practical situation. So do you remember that stuff? And we could use algebra, or we could use technology to fit that line of best fit. Remember, by just trying to put our line through, or using technology, least squares regression. So just check that you remember that stuff. But I've got a question for you, red hot burning question here. What if the plot is a curve? How would you fit a curve to a set of points? And in this presentation, we're going to look at two different possible models or mathematical functions which would produce a curve. And the first of them is called an exponential function. That's over here. We've got some number multiplied by a base raised to a power. So this is called an exponential function. We're going to look at this in some detail in a minute. And it's an exponential function because the variable, the unknown, is in the exponent. Here it is up here. X is sitting up as a power. And we've seen this before. If b is bigger than 1, it's going to be an exponential increase. You're going to be multiplying by a bigger and bigger number. You're going to be multiplying a number bigger than 1 over and over more times. It's going to grow. If it's a fraction in here, and you raise it to a power, you multiply it by itself over and over, it's going to get smaller and smaller. A half by a half is a quarter. By another half is an eighth, getting smaller. Okay, so that's the exponential function, and we'll catch up with that in a minute. And over here, what have we got? We've got powers of the variable, and a half power there, square root. So this is called a power function. And this one is interesting because, of course, if you're raising 0 to any power here, it would be 0. So they all go through 0, 0. Whereas over here, look at what they do. If you raise your base b to x is 0, b to 0 is 1, so you would get the point a there. So when x is 0, the value of the function is a. So they have got quite different characteristics, but they are good candidates for modelling curves or data which have produced a curve. And that's what we're about now. So if the plot is a curve, how do we handle it? Come on down, let's have a look. And one of the things we could do, could we make the curve a straight line by looking at the algebra of the function? If we could, then we could use y equals mx plus c. Couldn't we? Let's take this plot here. It's a straight line like before, and this point's not quite on it, but we could do a y step over an x step here, or change in y. Remember, delta means change in maths. Change in y over change in x, and the slope or the gradient, change in y over change in x, is, what's this y step? Well, it's approximately 15 take 5, so it's approximately 10. Of course, we could use technology. We used technology before and had a least squares regression line fitted more accurately, and the x step here is 2. So the gradient or slope of this line is approximately 5. Okay, we could do it by hand like that, and then we could say y equals 5x plus c, and we know c is the y-intercept, and we go across here, and it's approximately 0. So y is approximately 5x in mx plus c land. Just remember, if you're going to do that, you've got to come back to the context and say, in this context, y is actually the variable s, distance with time, something like that, and go back to that. It's all right to work in y and x land, y equals mx plus c, but we're doing modelling. So it's very important to relate our mathematics as a description to the practical situation. So we've got to use the variables involved there. All right, so if we could make it a straight line, we could use the same ideas as before, including technology. So let's have a look at these functions. And the first one we might look at is the exponential function. Exponential function where we have some number, a base raised to a power. So an exponential law or function is where the variable is in the exponent position. And if, as we said before, if the number being raised to the power is bigger than 1, something like 2, 3, 4, as you raise it to higher and higher powers, it's going to increase. So it's going to be an increasing function, starting when x is 0 at b to the 0 is 1 at a, what we just discussed. And if it's a fraction, a half or a third or something like that, as you raise it to higher and higher powers of x, it's going to decrease. Okay, so let's have a look now at this function. And if we use logs, you remember logs are powers. Okay, so we're going to take the log of both sides of this exponential function, and we'll use base 10 here. So log of y is a log of ka to the x, and this is a product, so that's the sum of the logs. Remember the log rules. The log rules are the same as the power rules because logs are powers. So it's log of k, and then it's log of a to the x, so that's x log a. Because you're raising a power to a power, you're going to multiply the powers together there. Remember, logs are powers. So if we separated this a bit, if we put this term up the front and said, well, x log a, let's write it as log a times x, and this number down the end. So this is a variable, y is varying, and so is x. So can you see this is like y equals mx plus c? And the screen clippings here are from Hayes and Harris publications, and they've used big Y and big X to show you that this is performing like a Y, only it's not little y because we're taking the log of y, and this is performing like your usual X here. So that would be linear. What's that saying? Let's have a look at what that's saying. If you were not to plot y up here but the log of y and x along here, this would be a straight line. What would its x-intercept be? Y-intercept be? It'd be log k, and the slope or gradient would be log a. So you could straighten out that curve coming from an exponential function by plotting it not with y's and x's, but log y and log y and x. And according to our algebra here, that would, if you like, straighten the line out. And that would make it easier for us to calculate the formula. Okay, so let's go down and have a look at the other one. In a minute, we'll do this for a start, what I've just said here. Log y against x would be linear for an exponential law, okay? The logs, taking the log of the expression and plotting log y against x would give you a straight line. And we could then work with that in the same way as we worked with straight lines before. All right, what about the power function? Here's the power function here, and we just talked about that. Let's come down a little bit more here. It's a power function because it's powers of the variable here. They all pass through 0, 0. Because if you stick 0 in here in any of these positions and you cube it or square it, it's going to remain at 0. So the simple power rules are like this: y equals x to the n, or k times x to the n. Could have some number in front to represent the whole family. Okay, so something like that. Can we straighten this out? Can we make a straight line here by using logs? Let's have a look. Using logs now, if y equals kx to the n, take the log of both sides. Log of y equals the log of the other side. So log y is the product here, so the sum of the logs, and then putting this one in front, the log of x to the n, a power expression, is n log x. Remember, your logs are powers. We're writing everything as powers, in this case of 10. And then we've got log k there. So now, if we look at it, we have a variable. It's not y this time, it's log of y. And we've got the other variable as log of x. So they're going to take the place of y and x in y equals mx plus c. And the slope is n, and the constant is log k down here. So it fits this sort of straight line idea if we plot it. Let's plot it now. And we're plotting it like this. This time if we put log y and log x, we would have a straight line. Okay, so this can be a nice little test to see what sort of function might describe that curvy nature best by checking out log y against x, and that should give you an exponential function, or an exponential function will give you a straight line under those conditions. And we could try log y against log x, and if that gives you a straight line, we know the curviness is due to a power function. Okay, so you're getting the idea. Have to think quite a bit about this. Okay, let's have a look at a little example here from Hayes and Harris. An experiment has been performed to find a law connecting variables p and t, and the graph of log p against t is given. So obviously they've left a bit out here. P against t was a curve up here, and then we're going to plot log p against t to see if that curve was due to an exponential function or a power function. So we'll start off with log p against t, and lo and behold, we get an approximate straight line. Okay, so let's try and find the slope of that. So we could take 2 points on it. We could take this one here, 0, 2.3, and this 3, 4.4. And it would be best to put 0, 2.3 there. Okay, so using the graph, the y step over the x step is delta y on delta x is 4.4, take 2.3, over 3, take 0, which is approximately 0.7 here. So here we would have the formula log p, remember it's not y up here, it's log p now, is approximately 0.7t plus 2.3. And 2.3 is the y-intercept, which we've read off up here. So this is by hand now. It's not as accurate as getting the calculator to do least squares regression on it. So therefore we're going to use these approximate signs here. We've got log p is approximately that. Now if the log of p is this, remember logs means powers, so this must be a power, because it's saying the log is this. So that is the power. So therefore p is approximately 10 to this, so it's 10 to the 0.7 to the t times 10 to the 2.3, because we're adding two powers there. So it's a product rule, or power rules in reverse if you like. It's a product of the two expressions. And so we can work out what 10 to the 0.7 is on the calculator, 5.01 to the t. So we have found, using basic straight line algebra, the formula connecting p and t. P is approximately 200 by 5 to the t. Right, not a bad trick, is it? You could also get the calculator to do that. What we're going to do at the first part here is to do it by hand and using our log rules. Right, let's do another one. Here's one where it was a curve and they've chosen to plot log n against log p, and it's come out to be a straight line. So in practice, when you had these curves, you would try both probably. We'll try some of those later on. We would try plotting log of one against the other, not no log, just the variable, and then we would, if we didn't get a straight line, we'd try the log against the log. Okay, so we're going to find the slope of the line, the equation, and so on. So let's have a look. You're going to try and find 2 points which by line of sight seem to be on the curve there. So this is the point down here, 0, neg 0.3, the y-intercept, and a point that's approximately on the line up there. So we want the slope now, y step 0.7 take neg 0.3, there it is, over 2 take 0. So it's a half. And c is approximately neg 0.3 as we read it. So y equals mx plus c. Y is not y now, it's log m we plotted up there to make the line straight, if you like, is a half. X is log p. We've got log p on the x-axis there. And then the y-intercept is neg 0.3. So we've got a rule, because we've straightened the curve out, if you like, by using logs. So there's our rule. Now the log of n is a half log p take 0.3. Do you remember your work with logs? We must write 3 as the log of something. We can't combine numbers and logs. So we can write 0.3 is the same as the log of 10 to the 0.3. So that's an important little trick there. Okay, 0.3 is the log of 10 to the 0.3. The power you raise 10 to get that number. Okay, so now we can change that to a number. We can also say it's log of p to the half, so that's the log of root p. Okay, so we've got to know those log rules. That's a log minus a log, so that's a division, isn't it? Subtraction of powers, logs of powers, remember? So the subtraction of powers means a division there. So n is approximately root p over 2. It's all approximately because of our reading off from the graph and from the approximate position of the straight line. So we've done it all with algebra, and that's pretty handy to get the idea there of finding the formula for the curve by getting a straight line using logs and working back with log rules. Fairly challenging stuff, but very useful. All right, come down and it's your turn. This time they're going to give you a set here. The first set is the log of y and just against the variable, and just using y and x there. Then just make sure when you put your formula down you are not in y and x land unless it's given to you. So here's log z and omega. That's a Greek letter, omega there. It's not really a w. And log of q. So make sure you write the rules at the end in terms of the particular context. Okay, so I think here you recognise that these are going to give you exponential functions, and these here with log against log should give you power functions. Now you're going to need quite some time to recall your log rules and to work through these. So I want you to do exactly what the examples are above. You might have to go back and look at those. You're going to find the slope of the straight line and the vertical axis intercept, or what's usually the y-intercept, and then the law using your rules of logs to remove the log expressions. Okay, so half a dozen there, and work hard on those, and I'll take you down to the answers now. Okay, there we are. So just go back and check that you can get all of those. That's very, very important. All right, let's move on and see what else we can do. So let's take a practical situation from the word go, if you like, from the very beginning. And here's some data, the growth of bacteria in a culture after the time of establishment, and that this is days now, and W is in grams. So if we were to draw that quite clearly, I think from this example, we're going to get some sort of curve. And what the book is saying here is we could check out log W against T and log W against log T and see which of them gives a straight line. So if we did that, and I'll show you how to do this on the calculator later, but if you did that by hand, you'd find the log of W and the log of T. And here, first of all, plotting the log of W against just T, and then log of W against log of T. So this one is not a straight line. So it's not a power function. It's going to be an exponential function. So because that's a straight line, we suspect an exponential law, where you take the log of the dependent variable against the independent variable, and it's a straight line. Okay, so now we could use some approximations here by drawing our line of best fit. I think it comes out pretty correct here. All the points are pretty much on the line. And so the y-step taking the point here 5, 2.07, and our intercept here approximately 8. I think they've used this one, that point and this point for y-step. 2.07 take 1.04, 5 take 1, the x step 5 take 1, and then we've got an approximate value of that. We use 3 significant figures, and here reading off the intercept is approximately 0.8. So it's all approximately. You can either use that sign to mean approximately, or this one here. So what have we just shown? The log of W equals, here it is, m slope by x, here is t, plus c, the vertical intercept. So therefore W is approximately, the log is this, so W is 10 to that power, because the log means a power of 10. Then breaking it up, it's 10 to this much times, because you're adding powers here, times 10 to the 0.8. Look on the calculator, get 6.3. And we look on the calculator, 10 to the 0.258, get 1.8. So we could write it as 1.8t times 6.3. We usually write it the other way around, 6.3 by 1.8 to the t, a b to the x if you like that, to the t, not to the 2, to the t. And then we can work out when t is 0, what was the starting weight, and of course it's 1.8 for the 0, which is 1, times 6.3 is approximately 6.3 grams. So that's a good way of checking, comparing the log against the ordinary variable, or log against the log of the variable, to see which one straightens the line out, if you like. Okay, I hope you've got the idea there. You might have to watch this a bit more. Now, I want to show you on the calculator, rather than working out logs individually, you can work out the logs and tabulate them on the calculator. I want to show you this. So turn your machine on here and go to stat mode. So we've got our list data here, the x value and the y value, just as they are. And then if you come across and highlight list 3, so move using this button, the highlight to that list 3. What we're going to do is now tell the calculator to put into list 3 the log of list 1, which is log x, isn't it? So how do you put this in here? With this highlighted, come down here and hit log, that log button, and it will appear here. And then go and find list. So list here is down in here. So you need to go shift and find list. Okay, and then 1. So if you do that and push execute, come over here to this calculator, and you can see in list 3 we've got the log of all the values in list 1. Okay, and we could do it again and tell the calculator to put in list 4 the log of list 2. So we can have the calculator listing all the logs of x and of y, if you like. So that's a good little trick. So just check that one out there so that you can make sure you're able to use the calculator to do that log work, rather than going through individually finding logs. Okay, so we've got the logs in there. Now what we could do is ask the calculator to do some plots. Okay, so let's have a look. We'll set the calculator up. Stat graph 1 is going to plot list 1 in the X list, and this is the log of list 2, so that's log of y. Oh, and it comes out to be a straight line. We're doing the same problem as what we just did up above. So if you then graph that, what we've done is list 1 is just the t value. List 4 was the log of list 2, so that's log of w. And you can see here it's a straight line. So you could, remember from before, you could hit calc and get this window where the calculator has actually fit a least squares regression line. So you could use this to write down the answer, which would be the log of w is approximately here. Now, what have we got? Ax plus b, this is approximately 0.256, the three significant figures, by t plus the b value 0.781. 0.781. Okay, so these numbers might be slightly different because it's a least squares regression line. It's been fitted more accurately than our line of sight one. So we can actually get the calculator to fit that straight line. Or let's have a look at the other one that we could draw to check it out. I'm just doing that previous problem in calculator land. So let's go to graph 2, and we're going to make the x list the log of x. So that's list 3, which was the log of list 1, and then the y value we're going to make list 4, which was the log of list 2. So we've got to keep our wits about us, which ones are which here, when we've found the logs of them. Okay, and then when we get this window, we'll just draw the graph. We won't bother doing calc. We won't bother trying to find what that is. It's not a straight line. So we're not going to use that one. So this is a quicker way, and we'll do some exercises on this in a minute. This is a quicker way of checking out, sorry about that. This is a quicker way of checking out whether the rule is exponential, so that's this one, or power rule, and this one didn't straighten out, so it's not this one. Okay, so get that idea here. So we can do it in that way, and then go on and work out the actual rule connecting W and T as we did before. So the calculator to the rescue there to do that straight line work for us. All right, do you get it? Fairly interesting stuff, isn't it? So here you are, you're meant to now do the same stuff again, but not by hand. All right, draw graphs here and use the calculator. Now in a test, obviously if they ask you to draw graphs, you have to put that down as hard copy as well. But just for now, you could just use the calculator and see which one is going to be straight and make a choice. Is it a power or an exponential law? Give evidence, so you need to talk about which one is straight, and then you can justify that or give further verification by trying to find the law as we did before. Once you have log W equals something times T plus the intercept, you've got to rearrange that using a log rule. So that's the hard part, and so on. So getting the idea of using the calculator to detect the type of law going by whether the log versus the independent variable is straight, or the log and the log gives a straight line. Okay, so pause the presentation and see if you can use the calculator now to determine what type of law it is and to get that actual law. All right, I'll show you the next couple here. 5 and 6. And 7 and 8, or the data for 8. There's 8. Okay, so have a go at all of those and toggle forward and look at the answers. Don't do them all and get them all wrong. As you do them, go and have a look at the answers now. So I'll show you those. So there's 3. Now notice here they haven't given evidence, so that the idea there is that this is not a straight line, but this one is, and then to get the rule, so check that out. Let's have a look at question 4. And question 5. Question 6. Come down a bit here. And question 7. And question 8. All right, just be careful here with remembering your stuff from before about whether things are a good model or not, and discuss those. Remember to talk about how well the line fits and also the R squared value. All right, let's go on. We'll just finish off with one little question, a little Huddy question here. And here's the question. Why would we use logs to straighten a line out? Surely technology could fit a curve to the set of points anyway, can't it? And the answer is yes. On the calculator are programs which will allow the calculator to get a line of best fit or a regression line through the points, trying to fit a power function or an exponential function. Let's go down and explore that. So this time we're going to leave logs out of it and make the calculator try to fit a graph. Okay, so here's our window. So we're going to ignore these log ones that we put in there. We're going to go back to the X list and the Y list. Okay, so it's just a straight graph. This one, this two, and we've got a curve. That's where we started. Then we tried to straighten that curve out, didn't we? Let's see if the calculator can fit a model, either an exponential or a power model, to that set of points. So we're going to ask it to do a calc. But this time, we're not going to try and fit a straight line because we haven't straightened the line out with logs. So we're going to ask it to fit various curves and see which one's the best. Come down, so it's the same set of data here. So here, I've split it into two. So here's our line, and if we hit calc, we get this window here. We're not going to try and fit a straight line, so we'll leave X. And we're going to go to the next window. Notice you can try to fit other functions here. I don't know whether you noticed that before. But go to the next window, which is this one, and there's the exponential function. So if we choose that, if we hit F3, okay, it gives us our options of how do we want to write our exponential function. So we'll choose this one here, a b to the x, because that's what we've been doing. So hit F2. It's done an exponential regression. Okay, it's fitted a line, a curve here to that set of data rather than a straight line. And it's given us the formula a b to the x. Okay, and if we hit F6 and draw it, we can see, hey, that's a pretty good fit. And we're going to compare our power fit in a minute. But you can see we have the rule here. So here the rule is y, and we'd have to go back into W and T land again, remember, y equals 6.03, and we should use approximately there, because we're rounding the figure off up here, 6.03 times x, and then, hang on, we're an exponential land, mate. Y equals 6.03 times, now b, our base, is 1.80 to the x, isn't it? And then when we come back and write our answer, we've got to put w or t or whatever the variables are in the context of the problem. Now, we could do that. Now, let's have a look. It looks a pretty good fit. But come down here, rather than fitting the exponential, what if we try to fit a power function? So hit F4, power regression. The calculator's working hard to fit a power curve to this, and it's not such a good fit. There's a point off here. And you could look at the R value or the R squared values in here and see a bit of difference there. Okay, so this one is better than this one. But what I want you to do is keep that in mind, but remember, you're looking for points on or near the line. Okay, are all points on or near the line? Are they randomly distributed? Same idea as fitting a straight line, fitting a curve, and then look at the R value or the R squared value in that order. Okay, so this time you're not going to do the algebra, you're going to make the calculator try and fit the best line of these options along the bottom here. Okay, and we're looking only in this presentation at exponential and power options. And to have a look visually at which is the best fit, that one or that one, looking at these points here, and then looking at R squared as well. Okay, don't forget to contextualize your answer at the end. Technology will use X for the independent variable, Y for the dependent variable. We must bring it back into context because we're doing mathematical modelling. It's a mathematical description of a practical situation. We can't stay in X and Y land. All right, that's a fairly challenging presentation, isn't it? There's lots of work there. And that's the last one in this series of modelling from data, law determination, and using your log expertise there to help out understand what's going on. All right, get rid of that, and hope to catch you in another presentation. It's cheers for now.